we have Pascal from Fraunhofer Institute to talk about what his exciting research is. A little bit about Pascal Halffmann. He acquired his PhD in mathematics in multi-objective optimization and later shifted to Fraunhofer ITWM in 2021, where he had his focus on quantum computing with a very strong background and focus on quantum optimization. Since the past 2 years, he's also the research coordinator for quantum computing and optimization at the Department of Financial Mathematics and took over the coordinator role for quantum computing for the Institute as a whole in 2024. This year, he is coordinating the entire project and the QSL partnership with Womanium, and we are proud to have Fraunhofer Institute as one of our key partners this year.
Thank you very much for having us here from Fraunhofer ITWM in Germany. It's really a pleasure to participate as a partner, as a mentor to this really awesome program that Womanium has drawn up here. So we are pretty happy to join in and also inspire young talent, but also get to know the young talent that is already out there. And we are looking forward to work with a couple of people from you, see what you're up to in the quantum world, and yeah. With that being said, let us first introduce what we are about at Fraunhofer. Yeah, thanks also, Vardaan, to your nice introduction to myself. So I can luckily skip the whole slide here. So as he said, so I'm maybe to wrap this up, I'm no quantum computing expert by training. Like I don't have a background in physics or like in computer science. I'm a mathematician, and well, so I was drawn to quantum computing after my PhD, where I was like at the point, okay, what's next? What is the next challenge after the PhD? And there was like the inspiring opportunity at Fraunhofer ITWM with the first quantum computing project, and I slid right in, taught myself into the quantum computing world, like read a couple of books, papers, and so on. And yeah, with this, I'm feeling a bit more quantum ready every week. But of course, there's so many stuff to learn that I think to feeling like really an expert, you need like a really good training, like you're getting here. So with this being said, let's dive in. What is Fraunhofer about? Maybe some of you have heard about us. So the Fraunhofer Society is based in Germany, and it's one of the world's leading applied research organizations. Um, so we are looking at technologies for the future and commercializing its findings in business and industry, and we are playing a major role in the innovation process by transitioning new innovative methods from research into the application. So we are like bridging the gap between like, okay, you have theoretical research results. What can you do with this in the real world? And we are providing this solution. And so we are trailblazer in trendsetter in innovative developments, research excellence. So we are doing research ourselves, not only research transitioning, and we are helping to shape our society and our future. And yeah, with this being said, some quick numbers about the society. So we have over 30,000 employees in 76 institutes and research institutes that are spread all over Germany, with a total business volume of 3.0 billion euros per year. So this is like really large society we're looking at here. And our funding comes mainly from industry contracts and public funded grants, but we are also part-time funded by the Germany's federal and state governments. So our research schedule is pretty impressive. We have over 7,600 patent families. There are like between 300 to 400 patent applications per year, and we are ranking among to the top 10 or top 20 most active patent applications every year. And yeah, we are an EU-wide leader in the establishment of standards here. We have 500 successful spin-offs since 2000. So there's not only the Fraunhofer Institutes, but also we have spin-off startups that we ourselves found or that we support. So we are also pretty successful here. And besides, of course, we're doing a lot of research. We have lots and lots of research projects. We have, of course, also we are working together with many partners from industry and research, like universities, international and national partners. We submit papers to conferences and journals, and I mean, I cannot give you the precise number here because, but I can assure you it will be a lot. So what is our mission or mission statement here? So our, like the Fraunhofer way, is guided through 6 principles here. So our first principle is that we want to contribute to a sustainable development through our research. This is like one of our main goals here. We want to do that with a well-balanced mix of excellent research and application. So we are not like pure researchers, we are not pure like consultants or applications helpers, but we are doing the mix. We see our clients not really as clients, but more as partners, and this helps us to develop integrated solutions for their success. Further, we are working together with the world's best in each topic to boost our own innovativeness, but also that of Germany and also of Europe. Our workplace is guided by constructive teamwork, diversity, and interdisciplinarity to create synergies that enhance our performance. And lastly, we have an excellent work environment here and autonomy to our research that fosters the employees' knowledge and enthusiasm for the applied research. So, as I said, Fraunhofer Society is spread over 76 institutes in Germany, and we are German-based. But this is not all. We are also international, with having lots of dependencies worldwide, being it in the UK, in the USA, Portugal, Chile, Sweden, Austria, Italy, or also Singapore. And further, we have representative office and partners in Brazil, South Africa, India, China, and Japan, among others. So we are not only, of course, our focus is in Germany, but we are also working on the whole world with international partners, and we have international offices all over the globe. So why is it called Fraunhofer? So what is our history? Why we are called Fraunhofer Society, not just the German Research Society? And this is due to this one guy here, Josef von Fraunhofer, and he was a researcher back in the 18th to 19th century who enjoyed equal success as a researcher. So he did a lot of research, actually. For example, the most famous one is those Fraunhofer lines that are the spectral of the sunlight, and he was the first one to measure those. But also he was an inventor and an entrepreneur. So he really made this transition from research, like deep theoretical research, towards the practice. So he was really doing like applied application-oriented research. And that is why he is like the perfect figure in the history that resembles the Fraunhofer way. And with that being said, our society has been founded in 1949. And since then, we have been successful all over the globe with our institutes. So how do we doing our research into practice? So there are different ways how we are doing this. So first of all, there's contract research, either by industry partners that can come to us and say, yeah, they want to have research for this and this topic, or we apply for research grant, for example, from from the National Funding Agency or some EU funding agency. Then we have, of course, the spin-offs or startups. We are also selling and providing intellectual property. We are also looking at standardization. For example, we have some DIN spec norms that we are applying to. We have knowledge transfer, for example, that we are providing teaching, but also consulting here. We have infrastructure service that is meant to improve the infrastructure around our institutes, for example, also by providing our roofs for renewable energies that also help our community around us. And at last, we also engaged in science communication. That is not, we are just not doing the science, but also we are presenting the science. And this is our impact on both the business and the society. Okay, so lots of stuff like more on the meta level, what Fraunhofer does, but maybe you want to know what actual research are you doing? Like, yeah, you can say how you're working, and so that's fine. But what is the actual research? And they have brought some research highlights of the Fraunhofer Society. And maybe let's start with the 1990s, because this was like really the place where Fraunhofer was like got like the real fame here. I mean, maybe some of you still have their old iPod, and I mean, what was one of the successes of the iPod was, of course, you didn't need that much space to save your favorite music, and this is due to the MP3 audio compression files data system, and this has been actually developed by Fraunhofer. So also one other highlight is the white light LEDs, which was like really important for today's displays. So these are like some really, I would say, most famous research highlights of the Fraunhofer Society. But since then, we are also pretty active in various spaces, being it computer science, chip design, also in the healthcare sector. For example, we have like these cancer therapy processes. Of course. We have also working, for example, for car manufacture, for example, here for having new rubber wheels. We have, of course, we are involved in AI, so we have voice assistants, and we are also helping transitioning to renewable energies, for example, by implying H2 technologies, for example, in the steel manufacturing departments. And of course, one that is most important for you, maybe, that we are also working on a high security quantum network, QNet, that is like the first German pilot network for tap and tamper proof data transmission. And I think that sums it up. So we are not just focused on one research area or one application area. We are widespread. As long as it's research transitioning to application, that is something that Fraunhofer is doing. And this is also true for my institute where I'm working at, the Fraunhofer Institute for Industrial Mathematics, based in Kaiserslautern, Germany. And what we are doing is we combine mathematical research with industry applications. So we are focused on everything that has to do with math. And for us, mathematics acts as a bridge between the research and the application here. And we are doing this with various topics like data analysis and modeling, machine learning, optimization and simulation, scientific computing and visualization. So this is like our focus, where we pick us out the results out of math that we try to transition to really helpful applications for the industry, for the society. And so one of key facts, so we are one of the largest mathematical research institutes in the world, actually, with 11 departments and over 330 researchers, together with lots of PhD students, student assistants, and so on. We are one of the largest research institutes that really apply mathematics for industry problems. And with that being said, we are also a member of the Fraunhofer Alliance in Quantum Computing that I will feature later in my talk. And the next one is, of course, I'm not just from the Fraunhofer ITWM, but also I'm from a distinct department, and I'm from the Department of Financial Mathematics that I also want to introduce briefly to you. And what we are doing here is we have 3 business areas that all circle around financial mathematics, which means stochastic simulation, data science, and quantum computing. And so we have 3 business areas. Of course, our main business area is in the financial services, where we focus on retirement provision, life insurance. So we are working together with insurance companies, banks, and so on, and fintech also. But we are also transitioning these expertise to other business areas, for example, accounting audit that we're doing for large car manufacturers, in healthcare, or for the public administration, where we're providing data science, for example, anomaly detection, to find frauds in your, for example, in your healthcare management. Then on the other hand, the financial market is of course closely connected to the energy market, where we have also lots of uncertainties due to renewable energies, and there we bring also our expertise in stochastic simulation. And these are our three business areas. On the other hand, we have three research areas. Of course, the one is already in the name of the department, which is financial mathematics. Data science I already mentioned, and the most innovative and novel research area is obviously the quantum computing. And quantum computing is now the right point because you want to learn about quantum computing, and that this is why you also want to learn about our quantum computing activities. So what does quantum computing do at Fraunhofer? Because quantum computing, to be honest, is rather theoretic. It's rather, I mean, we don't have like quantum utility yet. I mean, it's still debated. So why is a research organization that is focused on application-oriented research interested in quantum computing? Well, the reason is we are not looking just for now, but we are looking for looking for the next 10 to 15 years. And there, this might change. And the idea is for us, we want to make quantum industry ready. So that means that if the quantum computers and the quantum algorithms are sophisticated enough to provide application, then we want to make the industry ready that it already can take over those new results. On the other hand, we want to be ready when quantum is ready, meaning that if the quantum algorithms are there, we have the right applications, we have the right transitioning to applications ready, so we can immediately use those quantum algorithms. And this is our idea at the Fraunhofer, and this is compatible with the Fraunhofer way. And this is why we are looking at quantum computing in general. And we are doing this by the Fraunhofer Alliance of Quantum Computing that has a wide range of application areas since several research institutes of Fraunhofer are involved. Kaiserslautern, the Fraunhofer ITWM is one of them, but there are many others with a wide range of applications like logistics, pharmaceutical and chemical industries, finance, energy, material science, IT, health, and many more. And we had exclusive access to the IBM quantum computer in Ealing, which was the first quantum computer located in Germany that was also worked on together with IBM and Fraunhofer. And we were really proud that we were like on the first adopters of this new technology. If you want to learn more about our quantum computing activities at the Fraunhofer Society, head over to the link down below. You will find lots of information about the different activities that are really countless. The idea behind this is still we are taking our expertise in each research institute, in each application area, and try to find, okay, is there a way how to apply quantum computing? And does the application make sense for quantum computing? So is there like a mutual benefit out of that? And this is why several institutes at our society check this, provide algorithms, and also provide application to improve this linking between the theoretic successes in quantum computing and the practical need for better computation. And this is also the way what we are doing at Fraunhofer ITWM. And what we want to do is make our applications areas quantum ready that are numerous. So what we are doing is we have found our gap in like the quantum computing research community. We want to identify use cases. We want to develop new algorithms and test new hardware to find like, okay, what is the best mixture of application, algorithm, and hardware that can solve your real-world specific problem. And we are doing this by several actions in our institute. I mean, the first one, and this is also why I'm happy to be here, we are also providing education on quantum computing for young talent and practitioners. So this is also why we are here, because this fits really well in our course. Then we are, of course, working on different application areas, material science, finance, optimization, image processing, but also we are taking a glimpse at the hardware because we are, for example, looking at compiler, so the middleware between hardware and software, which is also something where we have expertise on the classical side, and we try to help out here to improve this transition. Also, we are involved in a hardware project where we are building a quantum computer based on Rydberg atoms, and we are providing the use case here. Also, if you want to know more, please head over to the link at the top. Yeah, and at last, I want to show you the quantum computing at the Department of Financial Mathematics, where even though we are narrowed down to a specific use cases and specific techniques, our application and research activities in the quantum world are still numerous, from building and benchmarking quantum AI, stochastic simulation forecasting, solving optimization problems, quantum circuit search, solving portfolio optimization, anomaly detection in business processes. So we have the whole pipeline from modeling to simulation to using algorithms from quantum optimization and quantum machine learning, and lastly, benchmarking these algorithms and testing out new hardware. And with that being said, let's finish off with a short glimpse at our projects in quantum computing in the department. You can find more information on the link above. So as I said, we have quantum education, but then we have several research projects in our department. One is the Enigma projects, where we are looking at hybrid quantum application for business processes. Like we have like a hybrid quantum classical system that we are looking at. Then we have the Enerquant project, where we are looking at quantum computing for the energy industry, for example, where we are providing a unit commitment for our power plants. That means a scheduling of the power plants for the next 24 hours. Then we have our quantum computing for finance project, where we, for example, simulate classical financial products like put and call options with the help of quantum computing. And at last, we have the quantum strategic asset allocation, where we are doing portfolio optimization via quantum computing. And the latest project we have is Quant2 AI, where we evaluate the performance of quantum AIs, like for the whole pipeline from the data until the result. And with that being said, I think I'm at the end of my time and also at the end of my talk. Thank you very much for your attention. And if you want to know more, you can also contact me, but also I think there's some time for some question and also answers. Thank you.
Okay. Yeah, thanks a lot, Pascal, for an amazing session. Thank you for giving a very good overview of everything that is happening at Fraunhofer Institute. I'm sure this must be very informative to the participants. I have a lot of questions on the Discord chat, and I encourage all people over here listening to it live to post their questions on Discord. I'll field them each one by one to you, Pascal. Before diving into the technical questions, a little bit more on the personal side, people are asking a little bit about yourself. So, Pascal, if you could share a little about your journey into quantum, because you mentioned you do not come from a traditional quantum background. What motivated you to start quantum, or how has this how has your journey been into quantum so far?
Well, I mean the journey. I mean it's like a really big learning curve you have at the start. I mean, quantum computing is, for me, it's like you mix together physics, mathematics, computer science. So, and I'm only mathematician, so there were like two new branches I had to teach myself. And as I mentioned, so I was really starting with zero knowledge of quantum computing. So after my PhD, of course, you have to transition back away from the university. You have to look for something new. And well, because I did my PhD in Kaiserslautern, it's a university, and we have a strong connection to the Fraunhofer Institute. And of course, I looked there and I saw, okay, there's something really interesting. What's quantum computing? And first of all, I didn't have a clue. And then I read some papers, some news about it. I mean, it was like 3 years ago. So okay, there was like the first hype train rolling over on quantum computing. So like there was like lots of information, lots of big news. And that was like for me motivation. Okay, I really can be at a point where I can really it's like a pioneering situation. It's like a gold rush. So this was like for me a motivation. You can start somewhere where you don't have to like search a lot for your like research gap that you can fill in, but you can like really steer and shape a new field. And that was like really interesting for me and a motivation to start. And also the interesting part there was that, I mean, I'm coming from optimization, and optimization is one of the areas where quantum computing is said that it can make a difference. But there was like those that are working on quantum optimization were like stemming more from the physics or computer science part. And I'm stemming more from the mathematician part. And I thought, okay, I could be a good addition to their expertise to learn from each other. So I can learn from them the depths of quantum computing while I can give them knowledge about optimization, like what are the classical optimization techniques? How can we transform them to work on quantum computing? And that is why I personally see my role here and why I focused on. And obviously, I mean, so back in the day, I mean, there were not that much of courses like we have here. So I'm really happy for all of you that you have like getting like excellent education here on quantum computing, because for me, it was like really starting with some abstract books where you first have to learn the bracket notation and then, go step by step. And it was like, besides my full-time job. So it was a lot of stuff to do.
Thanks a lot, Pascal, for sharing that. And I'm sure this might be very, very inspirational to a lot of students present on cohort. From the students, there's a common question which is quite often asked. Is the PhD at all necessary for diving into the quantum industry? Or can students with a master's degree or a specialization in quantum computing can also join the industry front?
I don't think that a PhD is necessary. It highly depends what you're looking at, like in which area you want to work on. And some, I would say you need like a lot of experience that maybe a PhD or something equivalent, like a long research activity, is necessary. But basically, you could start really after your master's degree if you already have some getting some insights during your studies in quantum computing. I mean, we always looking for new employees, new partners, and there are not many out there. And we would be happy if people are really engaging just after their master's degree. That would be like really helpful for us as well.
Wonderful. And on that note, if there are students who are interested in working with you or joining the Fraunhofer Institute in general, what is the process like? Are there general applications they can fill out too? Is there a proper admission cycle? How do the students go about joining the Fraunhofer Institute?
Well, I can only speak for the Fraunhofer ITWM. There are different like calls out there where you can apply. For example, if we are looking for like a specific researcher that is necessary for a distinct department or distinct project in our site, but you can also apply initially, like yourself, without any like application call out there. And well, I mean, the application is pretty standard. We need like a motivational document from your site. We need like a CV, maybe also some references or diploma or some equally important documents. And afterwards, there will be like a first call between us where we just try. We will just talk, like to see, okay, is there like a match? Do we speak like the same somewhat called language? And afterwards, there will be like a task for you that you have to prepare. Like, for example, you have to build a VQE for a distinct problem, and you have to solve the problem using variational quantum eigensolver. And then the task is to you not only solve the problem and solve the task, but also present your results to the audience. And the audience mainly consists of our members of our department. And you also have to present like a short pitch about an innovative research or application idea you would like to see that we pursue on our department. And this gives us like a nice impression about your innovativeness, but also on your way to present your results, because this is really important when you're working in the application.
Absolutely. Yeah, and I'm sure there might be a lot of applications coming your way after today's session, but also another opportunity because you are partnering with Womanium for the Quantum Solutions Launchpad and the fellowship opportunities. Just to mention this out here, there will be a project offered by Fraunhofer Institute at the very end of this Womanium program, where you all are expected to participate. And the winning team or the selected few best participants will get an opportunity to actually work with the best scientists there with Pascal and his team. So that is also an opportunity open for you. Coming back to the questions on Discord, moving to a little bit more technical side, participants are curious because you mentioned a lot of applications. They're curious, are there any applications where you have already found an advantage over the classical systems? Like you mentioned QML, financial applications. Are they already better than the classical benchmarks, or are they competing against them? What is the current industry standard?
So speaking from our side, I have to be brutally honest, no. So there is not yet. We have found like a quantum utility or quantum advantage in our application areas. We see signs that this might be possible. We have theoretic foundations that also can prove that this is possible, or this is indeed the case, that we have like a utility or even an advantage over classical problems here. Both, for example, in specifically in the image processing part, but also in the simulation part. For example, when it comes to Monte Carlo simulations, we have provable utility there, provable advantage there, but no utility yet. And this is due to the fact that, of course, we are only working on the software side, but also the hardware side has to be kept up. And this is, and also not just the hardware, but also the middleware and the algorithms as well. And with that being said, the whole product, I mean, it's not just you have a quantum computer that can solve it all from it by itself, but you need like all the way around, and everything has to click. And this is not the case yet. So this is like the problem where we're seeing, okay, we don't have an advantage yet. We have maybe some advantageous computational hardware. We have some advantages on the algorithm or software side, but yet we cannot like fusion those advantages together to have like an actual end-to-end advantage. But we are working on it, and feel free to support us in this endeavor.
Absolutely. Another question on a similar side of answering. When you talk about applications and practical applications of quantum computing, one very important factor to take into consideration is that the hardware is still very noisy, right? We are still in the net era where the machines are not perfect, as we would call them. So how do you deal with that? And I think we can separate two questions out here. Number one, on the software side, how do you deal with error mitigation techniques or error correction techniques? And second question, is there work at Fraunhofer also happening on the hardware end? Like, are you also working on improving the current qubit modalities and improving the current quantum hardwares?
Okay, so regarding the software side, we are already working with error correction and error mitigation techniques, obviously, because without it, you cannot do very much currently. It is clear that still using these techniques, our capacities for like the or like regarding the size of real world problems is rather limited. That is why we are currently working with toy examples and like shrunken down examples to that mimic somewhat the intricacies of the real world problems, and so that we can still grasp like those difficult details in the problem and the application part, and we try to solve these on the NIST device. And yeah, so what we are hoping there is that, of course, if the hardware scales, then also our solution will scale as well. One part to overcome this, for example, in optimization, is that we are using hybrid algorithms. So we have classical and quantum machines that work together, where we can solve larger problems because we can cut our problems into smaller pieces and getting the solutions here quite easily. So this is something what we are currently doing, because I mean, to be honest, I mean, real practical examples, for example, for portfolio optimization with 10,000 assets is not possible on a quantum computer yet on its own, and this is why we are having some tricks up our sleeve to overcome this issue, and we can say, okay, we have smaller problems, but for the perspective, we see that we have some advantages. Regarding the hardware side, we are also in the Fraunhofer Society, we are also involved in building quantum computers. I know, for example, from colleagues from the Fraunhofer IOF in Jena, so in the eastern part of Germany, they are working, for example, on a Gaussian boson sampler together with the university, which is a special quantum computing device such as the quantum annealer by D-Wave, but it makes use of the so-called Gaussian boson sampling, where we have an exponential speed up to solve this boson sampling compared to classical machines. And of course, this could really be interesting because this advantage is same as Shor's algorithm proof. So this is proven. And of course, they are working together with them. In our institute, we are connected to the RIMAX project, where we are working on a quantum computer building. In this project, a quantum computer is built based on Rydberg atoms. I mean, we are not providing the hardware, but we are providing rather the software for the hardware, like the transpiler, like also the use case and the algorithms, how to cope with this special quantum computer.
Wonderful. Yeah, thanks a lot, Pascal. Once again, there's a lot of questions on Discord. People are very excited by your talk today. But in the interest of time, I would like to wrap up today's session. What I'll do is I'll just filter out the best questions from our chat and mail them over to you, and you can take your time, respond them, and we'll disseminate them within the participants afterward. Thanks a lot, Pascal, once again for your session today. And yeah, hope you have a wonderful day ahead. Thank you.